Let's start by talking about how the graph of a function is affected by itself, its derivative, its second derivative being either bigger than, less than, or equal to 0. So I've made a big table here, and we're going to fill it in. In this table, we have these three conditions, being positive, negative, or equal to 0 at some value c. And then we're just going to see what that means when each of these functions has that property. So when the function is positive, that simply means that it's above the x-axis. No surprises there. And similarly, when a function is negative, that means that it's below the x-axis. And when a function is equal to 0 at a particular point, that just means that it crosses the x-axis at that point. And there's a few different ways that a function can cross the x-axis. It might go through it like that. It might be increasing and go through it like that. It could go down and just touch the x-axis from either side. So there's a few different possibilities there. Okay, what does it mean when the derivative of a function is positive? So the graph I'm going to draw here is the original function, right? That means that the function is increasing when the derivative is positive. We've seen this before. If the tangent line has positive slope, that means that the function is pointing upwards. It's increasing. And similarly, when the derivative is negative, that means that the function is decreasing. The tangent line has negative slope, so the function is decreasing. What does it mean when the derivative is 0? Well, then that's what we call a critical value. Right? That's what it means when the derivative is equal to 0. That means that we have a horizontal tangent line and potentially a local minimum or a local maximum, but not necessarily, as that counterexample of x cubed has shown us. So I'm not going to draw any pictures here because we're going to get to this square a little bit later on. There's going to be, in fact, a whole table of possibilities that tells us what happens here. So hold on and wait for that. All right, now finally, what does it mean when the second derivative, remember that's the derivative of the derivative, what does it mean when that is positive? Well, the second derivative being the rate of change of the derivative, that's measuring how much the slope of the function is changing. So if the second derivative is positive, it would take a negative slope like this, and it would make it larger and larger and larger, and eventually force it to be positive slope. It would create that shape. We call that shape concave up. So that's an important new concept. I'll abbreviate that as CU. Concave up just corresponds to the second derivative being positive, and it's any shape like this where you're sort of curving upward. So here we're concave up, here we're concave up. The opposite picture is called concave down. That corresponds to the second derivative being negative. Why does the second derivative being negative give us that shape? Well, if we start with a positive derivative, positive slope, the second derivative being negative is going to force that positive slope to get smaller and smaller and smaller until eventually you have negative slope over here. So concave up and concave down, those correspond to the second derivative being positive and negative. Positive and negative second derivative give you concave up and concave down shapes. And again, when the second derivative is equal to 0, you might have what's called an inflection point, where you change from being concave up to concave down, but that doesn't always happen. It's a little bit complicated. So I'm going to leave this square blank as well. We'll get back to it later on. Okay, let's see these ideas in action. I'm just going to draw the graph of some random function. All right, here I go. That looks good. So that'll be our function f of x. And we can see where the function is positive or negative. That just means it's below the x-axis or above the x-axis. But what I'm more interested in here is where the first and second derivatives are positive and negative. So what I'm going to do is I'm going to draw a new copy of the x-axis, like that. And I'm going to notate where, first of all, the critical values are. So let's just go through the graph. We'll use red for critical values. And I'm going to make a little dot anywhere that the tangent line is horizontal. Anywhere where the derivative is 0, that's a critical value. So in our color coding scheme, a red dot will correspond to a critical value. So that's a spot where the derivative is equal to 0. That's what that means. And now let's put those on this new copy of the x-axis like this. So we have these 5 critical values. And now let's draw in whether or not the first derivative is positive or negative in between the different critical values on these various intervals. So here, before the first critical value, the function itself is decreasing. It's moving downward. That means that the slope of the tangent line is always negative in that region. First derivative is negative. Here we're increasing, so we'll have a positive derivative. Then we decrease again. That'll be a negative derivative. But now check out this critical value. That's not a local max or a min. That's kind of a funny critical value where you just flatten out for a second and then continue to decrease. So here the first derivative is still negative, corresponding to this region of the graph, decreasing. Here we're positive, corresponding to this increase, and then finally the rest of the graph after the last critical value has a negative first derivative. So again, these negative and positive first derivatives correspond to the function increasing and negative. That should be decreasing. Pardon me. Trying to write decreasing there. And positive here, that'll correspond to increasing, decreasing, increasing, and decreasing. Okay, the function's going up and down. Let's play the same game for the second derivative. What can we read off of the graph about the second derivative? Okay, well, first of all, I'm going to go through and I'm just going to find the spots where the concavity changes. These are called inflection points. So here, this is all concave up. It's upward shaping. It's this upward facing bowl. But there's a spot right about there where the concavity changes. What do I mean? It's changing from being concave up to concave down, right? This is downward facing. So that change in concavity will correspond to the second derivative being 0. So I'm going to accumulate all these spots where the second derivative changes sign, where it goes through 0. There's another spot. At this spot we change from concave down to concave up. And now this critical value is also a so-called inflection point. An inflection point is one of these spots where we change concavity. Here we're changing from concave up to concave down. Here we're concave down. And now there's an inflection point. Well, it looks like it's just about on the x-axis right there. So that's again a change in concavity. Here we're concave up. And then right about there we change to concave down. And then we're concave down the rest of the graph. So let's do the same thing. Let's put in pluses or minuses according to whether the second derivative is positive or negative. Remember that positive corresponds to concave up, negative corresponds to concave down. So those will be your positive or negative values for the second derivative over those various regions. And again, these purple spots where I've drawn a purple circle, those correspond to inflection points. These are the inflection points of the graph. That's just where the concavity changes. Okay, so let me write below. It looks like you can't quite see everything in one shot, but that's okay. I'm going to write CU for concave up, CD for concave down. So now we have a complete analysis of this graph in terms of the first and second derivative and what those values for the first and second derivative mean geometrically. To finish the graph off, let's go back up, and out of the remaining critical values, let's circle the local maxima and local minima. So locally, these two spots are bigger than anything nearby. We'll use gold for local maxima. And then we'll use light blue for local minima. There's two local minima on the graph. So remember, a critical value, it could be a local max or min, like these 4 points, but it could also not be a local max or min. It could be an inflection point, like that point right there. Okay, let's now think about how to detect these local maxima and minima. And if you look at the sign of the derivative, you'll notice a pattern. The local minima, they occur where the first derivative goes from negative to positive. That corresponds to that change in direction. Same here. First derivative is going from negative to positive at that local minimum. Conversely, the local maximum, those happen at a critical value where we change from positive to negative first derivative, where we change from increasing to decreasing. Same for this one. We change from positive to negative. So that's a general fact. It's called the first derivative test. So suppose that we've found a critical value of our function. Remember, that just means that the derivative is 0 at that point. If the derivative switches from a positive value to a negative value at that point, then that critical value is a local maximum, right? So if the first derivative is positive, we're increasing. If the first derivative is negative, we're decreasing. And in between, we must have kind of plateaued out at some mountain peak. We have a local max at such a point. Similarly, if the first derivative switches from negative to positive at a critical value, then we have a local min. So negative first derivative, we're decreasing. Positive first derivative, we're increasing. In between, we've bottomed out at a bottom of a valley. We have a local minimum. So those are the two important cases of the first derivative test. These are ways that, given a critical value, somewhere where the first derivative is 0, we can determine if it's a local maximum or local minimum. But there's two other cases to the first derivative test. Here they are. These two other cases of the first derivative test are cases where the critical value is not a relative extremum, where it's not a local max or a local min. And that corresponds to the situation where the first derivative stays positive, so that we just increase right on through. First derivative is positive, positive, positive. It becomes 0 just for a second, and then it keeps on increasing. It's not a local max or local min. And then if the first derivative is negative both before and after the critical value, that's just the symmetric thing where we're decreasing. So in these cases, you'll notice that I've circled it with a purple. That's because these are both inflection points, right? Notice that we change from concave up to concave down. Here we change from concave down to concave up. So that characterizes these critical values that are not local maxima or local minima. Let's see that first derivative test in action. We're going to use it to find all relative extrema of this function x cubed times e to the 4x. Remember, relative extrema, that just means all the local maxima, all the local minima. So we first got to find the critical values. We've got to figure out where the derivative is 0. So we have x cubed times e to the 4x. This is going to be a product rule. So if we take the derivative of the first function times the second, we'll get that, plus the first function times the derivative of the second function. When we take the derivative of e to the 4x, using the chain rule, we'll have a 4 come downstairs, right? So e to the something is its own derivative, but then the inside function has derivative 4. So that comes from the product rule, and then the chain rule for the second piece. Okay, let's clean that up just a little bit. Notice that there's a common factor of x squared e to the 4x in both of those terms. So that leaves 3 in the first term, and it leaves 4x in the second term. That's going to be handy because to find the critical values, what do? You set the derivative equal to 0, right? Critical value means the derivative is 0, so you want to figure out where that happens. And then you solve for x. Here we go. So we're going to set this expression, x squared e to the 4x times 3 plus 4x. We're going to set it equal to 0. All right, now check it out. E to the 4x, the exponential function, its outputs are always positive. That's never going to be 0. So the only way that this function, this expression can be 0 is if that x squared term is 0, or if that term is equal to 0. One of those two must be equal to 0. So either x squared is equal to 0, or 3 plus 4x is equal to 0. So in the first case, the x value is obvious. It's just 0. What about 3 plus 4x? Well, it's the same thing as 4x equals minus 3. And so the other critical value is minus 3 over 4. Those are the critical values. Now we need to determine whether these critical values are local maxes, local mins, or neither, and we're going to use the first derivative test again. So let's use that first derivative test. I just draw a little kind of picture of what's going on. And here's minus 3/4. Here's 0. And we're just going to test at particular points on either side of these different critical values. So here's a nice easy test point. How about minus 1 to the left of minus 3/4? And then we could use minus 1/2. That's in between minus 3/4 and 0. And then we could use, I don't know, how about just 1 to the right of 0? Which numbers you choose isn't so important, just something that you can actually compute. Okay, so now we need to plug those into the derivative, not into the function itself, into the derivative to figure out if the derivative is positive or negative. So I'm going to use the formula for the derivative that we had before after I had factored it. So I'm plugging in x into our formula for the derivative from before. Minus 1 squared is 1. That's because 2 wrongs make a right. We have e to the minus 4, and then we have 3 minus 4. That's the important term there in parentheses. We get minus e to the minus 4. That's a negative number. So that means that because it can't be 0 anywhere to the left over here, the first derivative is negative for all of those values. Okay, next let's plug in minus 1/2. What happens then? So it'll be e to the 4 times minus 1/2, and then we have 3 plus 4 times minus 1/2, like that. Minus 1/2 squares to 1/4, and then we have e to the minus 2, coming from 4 times minus 1/2, and then we have 3 minus 2. Notice that 4 times minus 1/2, that's just minus 2 there. And so we end up with 1/4 e to the minus 2 times 1. That's a positive number. You might think it's negative because of the negative in the exponent, but remember, e to the minus 2, that just means 1 over e squared. That's a positive number. So the values in between minus 3/4 and 0, the values of the derivative, they're all positive. The function is increasing there. Finally, let's plug in 1 into the formula for the derivative. This one's a little bit easier to plug in for. We just get e to the fourth times 7. 3 plus 4 is 7. That's the important term. The term in parentheses. Notice the term in parentheses determined the sign each time. That's also positive. Okay. So there we have figured out the signs of the derivative. What does that mean about the function? That means the function is decreasing, and then it's increasing, and then it's still increasing. Okay? So what in the world could that mean? Well, actually, if you look at the graph of this function, it looks something like this. Okay? So it's below the x-axis, it's decreasing. It has a little bit of a local minimum right here at minus 3/4. That's where it changes from decreasing to increasing. So now it's increasing, but only ever so gradually, and then it kind of shallows out for a second at the origin. That's what this critical value is doing. But then it starts shooting up to infinity really fast. So that's just a rough sketch of the graph of this function. And the critical values we found were at minus 3/4 and at 0. And now as we can see, because it's first derivative test, decreasing then increasing, this one is a local minimum. But this one at the origin is not a local minimum or a local maximum. It's neither. It's actually an inflection point. Just to the left there, it's concave down, but here it's concave up. We don't really need to say for this problem that it's an inflection point, but it is true. The main conclusion is that it's not a local max or a local min. This is the only one. So that's the answer to the problem. The only local minimum or local maximum is at minus 3/4.